Welcome to the Deep Dive. Today we're embarking on a really fascinating exploration into the world of black powder.
That's right. You asked us to dig into how it's made, the safety side of things, which is huge, and how it's tested.
Exactly. And for this, we've got a pretty substantial resource. A detailed book all about black powder production, testing, optimization, the works.
And it covers history, too, like the commercial side in North America.
Our mission here is to pull out the really crucial, the most interesting bits for you, give you a solid grasp without drowning you in technical jargon.
And what's really cool, I think, is that black powder seems simple, right? Just a mix of stuff.
Yeah, 3 ingredients.
But the how and the why behind making it good and safe, that's surprisingly complex. We'll get into some history, some safety stuff that might make you think twice.
Prepare for some aha moments, maybe.
Hopefully, it's more intricate than it looks.
Okay, let's dive in. So our source highlights this shift, really, in how people approached making black powder.
Yeah, it talks about moving away from, let's say, late 20th century amateur pyrotechnics,
Right.
which could be a bit rough and ready,
Right.
towards something more refined, more knowledgeable heading into the 21st century.
So like a more scientific approach?
Kind of, yeah. More evidence-based, better understanding of the principles, and a bigger focus on safety and consistency.
And speaking of safety,
Wow.
that's a huge theme. It kicks off with this pretty startling claim
Oh, yeah.
that black powder can actually be more dangerous than dynamite or TNT or even nuclear warheads.
That does grab your attention, doesn't
It
it?
really does. What's the reasoning there?
It boils down to how easy it is to ignite. It just takes a tiny spark, a single spark.
Just one.
Yep. Whereas your other explosives, they generally need a much bigger nudge, like a blasting cap or a specific trigger.
Okay, so it's hypersensitive to sparks. What kind of sparks are we talking about? Not just open flames, I assume?
No, the book really emphasizes static electricity. That's a big one.
Static, like shuffling your feet on carpet?
Exactly. Or just handling materials in dry air. The book even mentions Colorado Springs. You know, Tesla's old stomping grounds as a place where static is a known issue.
Huh. Interesting. What else?
Friction, obviously, rubbing things together. And just basic electrical contacts, faulty wiring, switches, that kind of thing.
So, practical tips.
Yeah.
What does the source say?
Well, things like wearing cotton clothes synthetics generate more static. Grounding your workspace is critical.
Right.
Being careful when pouring powders to minimize friction. Grinding potassium nitrate separately from the other stuff. Basic precautions, but vital.
And it doesn't stop there, right? The
Wait,
book
wait,
talks about wet black powder, too. I would have thought wet is safer.
You'd think so, wouldn't you? But
He-
the author shares the story, calls it a whoosh incident.
A whoosh incident.
Yeah, got burns on his fingers from handling wet black powder that ignited unexpectedly. While it's generally less prone to spark ignition when damp, if it does ignite, it can still burn surprisingly fast. Water doesn't make it harmless.
That's counterintuitive.
Mm-hmm.
The book also talks about complacency, doesn't it?
Yeah.
These great green gurus.
Yes. Complacency is a killer. You do something risky 100 times, nothing happens. So you think the 101st time is fine, too.
Until it isn't.
Exactly. And the gurus, well, these are folks who might talk a good game about safety, but then maybe behind the scenes or even boastfully cut corners.
That sounds dangerous, especially if people look up to them.
It's incredibly dangerous. It normalizes bad practice. The book really hammers home, stick to the proven safety rules, no matter what someone else claims they got away with.
Another big warning. Don't work alone. Makes sense if you have an accident.
Right, but it's more than just having someone to call 911. The book points out something pretty sobering.
Which is?
If emergency responders arrive and there's any hint of explosives or pyrotechnics, things slow way down.
Oh, like they call in the bomb squad.
Potentially, yeah, or they secure the area first. Point is, you might not get medical help nearly as quickly as you would for, say, a heart attack. It's a different kind of emergency for them.
That's a really grim but important point. And then there's a simple idea. Speed kills.
Absolutely. Powder that burns super fast might be desirable for some things, but it's inherently riskier to make, to handle, to store.
So err on the side of caution.
Pretty much. Is that extra speed really worth the extra danger? Often, maybe not.
The book also brings up the idea of fallout, right? Not just the physical kind.
Yeah, thinking beyond the immediate blast or fire. What are the legal consequences? Social consequences, especially if you're doing this near other people.
And it mentions the irony of calling anything involving this perfectly safe.
Right. Even cites a DuPont patent that used gasoline in the process, described as perfectly safe, which
Yeah.
is
Gasoline. Okay, that sounds great.
or crazy. It underlines the inherent risk. And it all leads to the idea of walking the walk. Don't just talk safety. Practice it consistently.
Makes sense. Okay, let's shift gears to the ingredients, starting with potassium nitrate, KNO3. Purity seems to be a big topic.
It is. You see very high purity figures like 99.8, 99.9% quoted by commercial makers or in pyro literature.
But the book says maybe that's overkill sometimes.
For general black powder making, yeah.
Hmm.
It suggests that super high purity isn't strictly necessary just to make it go bang.
But there's a catch.
Well, impurities, especially chlorides, can make the powder attract moisture over time. So for long-term storage, higher purity is definitely better.
So function versus longevity.
Kind of. You can get different grades, technical, fertilizer grade, even food grade. The book says they'll all work to varying degrees.
Food grade, like for curing meats.
Yeah, but the potential issue there is unknown additives. Food grade might contain salt, for instance, which you don't necessarily want.
So you don't absolutely need lab grade stuff to start.
Not necessarily, though the implication is clearer. Pure usually means more reliable, more consistent, better shelf life.
Got it. Okay, ingredient number 2, charcoal. And this is way more than just BBQ leftovers.
Oh, absolutely. Charcoal is mostly carbon, sure, but it also has these things called volatiles.
Volatiles?
Yeah, leftover organic compounds from the wood. And they have a huge impact on the burn rate. The book suggests around 25% volatile content is kind of the sweet spot.
So it's not just the carbon fuel, it's this other stuff too.
Exactly. The volatiles help it ignite easily and burn quickly. It's a balance. And the temperature you make the charcoal at, that controls this balance.
How so?
Higher carbonization temperatures give you more pure carbon, but drive off more volatiles. That can actually make the charcoal harder to ignite.
Interesting trade-off. And what about graphite? Do you accidentally make pencil lead?
Huh. No, not really. Graphite forms at much, much higher temperatures, like over 2000 Celsius. Way hotter than you typically use for making charcoal for powder.
Okay, good to know. Now, the book really dislikes briquettes, right? Like the stuff for grilling.
Hates them. Yeah, for black powder, they're apparently terrible. Multiple reasons. Usually hardwood, which isn't always ideal. They have binder starch, maybe coal dust, other stuff to hold them together. High ash content, possibly clay or lime from processing. Could even have unburnt wood or chemicals. Just avoid them.
Message received. Steer clear the BBQ briquettes. What about willow? Isn't that the classic, the best charcoal?
That's the legend, yeah. Willow has this long-standing reputation.
Yeah.
But the book says modern tests show other woods can actually perform better. Plus, willow isn't just one thing. There are tons of different willow species, and they might vary.
So tradition isn't always right.
Seems like it. Woods like trembling aspen and buckthorn get high marks in some tests mentioned.
And activated charcoal. That sounds like it might be good. Extra surface area.
It can make things react faster initially, yeah. But the activation process, it strips out those vital volatiles we talked about.
Ah, so maybe too much of a good thing.
Could be. And not all activated charcoal is even from wood. Some is made from coal. So maybe not ideal for balancing performance.
The book lists a whole bunch of other woods too, right? Aspen, balsa, so maybe unfounded claims there.
Bamboo.
Yep, bamboo's okay, but high ash. Beech, buckthorn, another top one. Hornbeam, horse chestnut, oak, sometimes good. Paulownia gets rated highly.
It's quite a list. It really shows that the wood source matters a lot.
It does. And the book even mentions people have tried finding substitutes for charcoal, like using certain organic compounds.
Any luck?
Not really. Nothing quite replicates charcoal's specific chemical and physical properties. It's pretty unique stuff.
So if you want to make your own charcoal, how do you get it right? Consistency seems tricky.
Super tricky. The book stresses that even in labs, controlling the temperature perfectly is hard. And temperature is key.
How do people control it?
Ranges from basic thermostats all the way up to microcomputer systems and more advanced setups. Getting even heating inside whatever you're using the retort is crucial.
You mentioned retorts. What are the other ways? Traditional methods. Yeah. Traditional ways include charcoal pits or mounds. Basically, carefully controlled burns and earth kilns. Tricky to manage airflow perfectly.
And kilns.
Hard-walled kilns exist too, like the Brazilian beehive shape or the U.S. Missouri type. Easier to load, less dirt contamination. But home scale is usually batch process.
The book seems to favor the retort method, though. defines it pretty specifically.
It does. External heat, minimal oxygen inside. That's the key difference from just burning wood in a pile or a simple kiln.
Advantages.
Loads. Cleaner charcoal, more consistent charring, usually faster, less ash, much better control over those volatiles, better for the environment, and you can scale it up or down.
Downside.
Maybe uses more fuel since the heat is external, but for quality it seems preferred. And a retort can be anything from a coffee can to a big drum, as long as it seals and takes heat.
Finding the wood. Any tips there?
Well, historically, people used coppicing cutting trees low to let them resprout small branches. That gave a steady supply of the right size wood.
And prepping the wood. Wet, dry, bark on, bark off.
Book says both wet and dry work. Wet just takes more energy to drive off the water first. Bark on or off seems to be debated.
And optimizing the charcoal is all about
Temperature control. Hitting that right temperature profile to keep the right amount of volatiles. That's the secret sauce. The author even mentions getting wood easily, like from pruning a peach orchard.
Right, so maybe sources are closer than you think. Okay, ingredients sorted, charcoal made, now mixing and incorporating.
Yes. And a key step here is using a saturated solution of potassium nitrate, dissolving it in water first.
Why saturated?
Gets the potassium nitrate really intimately mixed with the fine charcoal and sulfur particles when you combine them, coats everything.
Then you have to get the water out again. Sounds tricky.
It is. Dry it too fast, the potassium nitrate can leach, meaning it moves around in clumps unevenly. Dry it too slow, you get large crystals. Neither is good for a uniform mix.
So how do you dry it properly?
Controlled drying is the goal. Starting with a hot saturated solution helps. Then maybe remove bulk water quickly, but do the final drying carefully.
What not to do? The book warns about some methods.
Oh yeah. Rapid heating, big fire risk. Slow heating in a sealed container after the water is boiled off, risk of hot spots, very dangerous. Even using vacuum cleaners is warned against.
Vacuum cleaners, why?
Sparks from the motor, maybe? Or just sucking fine powder into bad places. Safer ways are spreading it thin on a large surface to air dry, or alcohol displacement.
Ah, the CIA method connection.
Exactly. That method uses alcohol to help pull the water out and precipitate the potassium nitrate finely.
We'll get to that. But first, pressing and granulation. Why press it?
Commercial makers press the damp mix mainly to control the density and make it consistent.
Does pressing make it burn faster? I thought denser meant faster.
That's the old belief, but the book mentions experiments suggesting the opposite might be true. Less dense, more porous powder might actually burn faster.
Huh. So you don't need a giant hydraulic press.
Maybe not. Moderate pressure seems enough. The author mentions discovering you could make decent pressed pucks just using a pasta maker, almost by accident.
A pasta maker. Okay. What about granulation? Making the grains. Sounds fiddly.
It's often the most dangerous step commercially, apparently. Less so at home scale, relatively speaking. Two main ways. Wet and dry.
Wet granulation.
Pushing the damp, press powder through a sieve. Using a wooden spoon is recommended, no sparks. Getting the moisture level just right is key. It avoids the leaching problems you get if you just let wet powder dry on its own.
And dry granulation.
Recommended for harder, denser powder. You do it after the pressed pucks are totally dry, which takes days.
How do you break up hard, dry pucks safely?
Rolling pin between sheets of paper is preferred, or light tacks with a non-metallic mallet, or very slow controlled pressure in a press. Gentle is the key.
Okay, now let's fully unpack this CIA method. Sounds cool, but is it real?
The name's real, the myth around it, less so. It wasn't secret agent stuff.
No, tell more.
It came out of research by Frankfurt Arsenal, that's U.S. Army Ordnance, looking into improvised weapons and explosives back in the day.
Ah, military origins. How did pyros get onto it?
It got published or details leaked out, and people interested in making their own powder saw it as maybe an easier way, less equipment needed.
Does it work well?
It can improve things, especially if you don't have a mill, but the book stresses you still get better results if you properly mill and incorporate the ingredients beforehand. It's not a magic bullet that skips fundamental steps.
So what are the pros and cons?
Pros. Accessible for entry level, doesn't require special gear for slower powders, maybe a bit lower explosion risk than some other methods during processing.
Cons.
Doesn't replace good milling for top quality, but combine it with ball milling, and apparently you can get propellant-grade powder.
How does it actually work? The alcohol part.
You dissolve the potassium nitrate in hot water, suspend the charcoal and sulfur in there. Then you add an organic, liquid methanol, isopropanol, ethanol, even vodka apparently works.
Vodka. Seriously.
Seems so. The alcohol makes the potassium nitrate less soluble, so it crashes out of solution as very fine crystals, coating the other stuff. Using plenty of alcohol and cooling it fast helps make those crystals smaller.
Then you get these pucks of material.
Right. You dry them carefully. Avoid direct sun when they're really wet. That can cause leaching. But some sun at the very end can help harden them.
And then granulate?
Yep. Crush the dry pucks, often with a rolling pin, then sieve to size.
Okay. Let's talk ball milling then. Seems common for hobbyists.
Very common for amateurs, yeah. Though not the main method, commercially they use huge wheel mills mostly.
What do commercial guys use ball mills for?
Mixing ingredients, pre-grinding before wheel milling, or tumbling finished sporting powders to glaze them. That's done without the grinding balls inside.
Safety must be a massive concern with ball milling.
Huge. The #1 warning is, do not mill all 3 ingredients, KNO3, sulfur, charcoal, together. That's called free component milling, and it's asking for trouble.
So what's the safer way?
Mill components separately, or mill charcoal and sulfur together, still risky, but less than all 3, or maybe KNO3 with just a tiny bit of charcoal. Small batches always. Watch for sparks, static. Use blast shields, remote controls if you can. Keep it clean.
Static electricity again.
The book calls it a stealth killer with ball mills. Very easy to get a static spark inside the mill.
Can you build your own mill?
You can, yeah. Simple, cheap ones exist, but they're often not very efficient. The book points towards resources for building better, safer ones.
Are there different types of mills?
Mainly jar mills, the common hobbyist type.
Yeah.
Barrel rotating horizontally. Planetary mills are more intense, faster, but expensive, and potentially more dangerous for black powder mix. Vibratory mills, too high energy, definitely avoid 3-component milling there.
What about the balls inside? The milling media? Does it matter what they're made of?
It does. Ideally, same size balls. Heavier is usually better for grinding. Hardness isn't super critical for black powder.
What materials to avoid?
Soft stuff like lead contaminates the powder. Lead shot is better than soft lead sinkers if you must use lead, but still not ideal. Glass balls, spark risk.
What's good then?
Ceramic media is generally good. Look for non-sparking types, but test it first to be sure. Surprisingly, wooden balls are sometimes used just for mixing, not grinding.
Can you tell if the mill is running right just by listening?
Apparently, yes, to some extent. Intermittent heavy thumps might mean it's overfilled or running too fast. A swishing sound could mean the media is just sliding, not tumbling. You want a continuous cascading sound that usually means it's mixing and grinding properly.
Fascinating. Shifting gears slightly, competition-grade powder. Sounds like aiming for maximum speed.
It often is, yeah, but the book has that stark warning again. Fast is not safe.
Right.
It really cautions against pushing speeds too high, especially mentioning that mixes heavy on potassium nitrate and charcoal, like 4.1 to 6.1 ratios, can be particularly dangerous.
Is there any way to make fast powder safer?
One approach mentioned is pre-wetting the potassium nitrate with alcohol or water before mixing.
Does that help?
It might moderate the reaction a bit, but downsides? You can lose some KNO3, alcohol costs money, and it's apparently messy and tedious, so trade-offs again.
Okay, what if you're trying to do this on the cheap? Any tips from the source?
Yeah, it acknowledges that laboratory grade usually means expensive. So look for technical or agricultural grade chemicals maybe. For charcoal, you can make small batches in simple retorts like coffee cans heated with a wood fire. Temperature control might be basic or non-existent there, though.
Cheaper alcohol.
Basic isopropyl alcohol, like 70% rubbing alcohol, is often cheapest and works okay for things like the CIA method.
Scales, sieves, temperature.
Accurate scales are essential, but cheaper digital ones exist now. Sieves can be homemade from tin cans or embroidery hoops. For temperature, BBQ-style dial thermometers or cheap thermocouples connected to a basic multimeter can give you a reasonable idea.
So it's possible to start without breaking the bank.
Definitely seems possible, yeah. Resourcefulness helps. Safety still has to be #1, though, regardless of budget.
Let's touch on the chemistry. You said earlier it's not fully understood, even after centuries.
Kind of amazing, isn't it? But yeah, research has been tough. Funding dried up as modern explosives took over. Plus, studying something that explodes violently makes collecting data tricky. And historically, testing wasn't standardized.
So we stick to the basics, the 751015 recipe.
That's the classic Waltham Abbey formula, yeah.
Yeah.
75% potassium nitrate, 10% sulfur, 15% charcoal. That's the benchmark.
What do we know about the reactions?
Well, KNO3 reacting with carbon makes potassium carbonate. With sulfur, you get CO2, potassium sulfate, potassium sulfide. Having all three together lowers the temperature needed for it to decompose or explode.
And the sulfur, what's its main job?
It does a few things. It increases sensitivity to impact, actually. Carbon reduces sensitivity. But sulfur is also really important for how fast the flame spreads through the powder. It's not just fuel.
Interesting. What about sulfurless powder?
That exists too. Stoichiometrically, it'd be about 87% KNO3, 13% charcoal. It's sometimes used in igniters, maybe with just a tiny bit of sulfur, like 2%.
Okay. The book mentions some other methods and historical quirks, too. Any weird ones?
Yeah. One idea that sucks, as the book puts it, was using a rapid vacuum drop to make crystals form. From an 1875 patent, trying that with a shop vac sounds like a terrible idea. There was a safer vacuum method proposed too.
And the DuPont gasoline thing.
Yeah, that's a really wild one. Using gasoline instead of water in a rod mill. Apparently they just didn't like using a liquid solvent, and KNO3 doesn't dissolve in gasoline, so...
Yeah.
Bizarre logic.
Definitely unconventional. Okay, moving towards the end. Testing. Why is it so important?
Because if you're making something, you need to know how it performs, right? And you need to be able to compare batches or compare your stuff to others, but you need good tests.
Good how?
Accurate, precise, repeatable. The book defines these. Accuracy is closeness to the true value. Precision is how close repeated measurements are to each other. Repeatability is getting the same results under the same conditions.
And the apples and oranges problem.
That's comparing results from different tests or tests done under different conditions. It's meaningless. You have to compare like with like. Historical tests have this problem too.
What were some of those historical tests like? Sounds like they could be pretty crude.
Some were. Ye old ancient and crude ways, as the book amusingly calls the earliest efforts. Then came devices called eprouvettes.
Eprouvettes.
Yeah, early gadgets to measure gunpowder strength, all sorts of variations. Hinged lids that blew open, ratchet mechanisms that clicked up notches based on force, spring-loaded ones, gravity-based ones.
Wow. Any other types?
Pistol eprouvettes were popular with artillery guys. Some could even fire a ball. And mortar eprouvettes, basically tiny mortars that threw a heavy ball, measuring the distance or height.
Were they any good?
They had issues. Sir Andrew Noble criticized mortar eprouvettes for having barrels too short to really represent performance. And tests showed different eprouvettes gave widely different results for the same powder. So consistency was a problem.
What else did they do historically?
Linear burn rate tests are probably the oldest, just timing how long a line of powder takes to burn. Simple, but maybe doesn't tell the whole story. DuPont had a quickness tester to compare burn rates side by side.
Closed bomb tests. Sounds dramatic.
Crude versions involved just burying a container of powder and seeing how big a crater it made. Later, they developed closed bombs with pressure gauges. The book shows a pressure graph from the Civil War era.
Okay, so testing evolved. What about modern methods?
Well, there's pyrogolf.
Pyrogolf, like hitting golf balls with explosions.
Basically, it's a modern mortar eprouvette. You launch a standard golf ball and measure its flight time or distance. Supposedly more user-friendly and accurate than old mortars. Lab versions have sensors and electric ignition.
Practical for hobbyists.
Probably not for regular batch testing. Needs special gear. Video cameras are useful, though, especially for slower burns. You can analyze frame by frame.
And electronic sensors?
Big area. Transducers convert physical things, pressure, temperature, speed, into electrical signals. Simple wire breaks can measure projectile speed. Temperature is tricky because it happens so fast. Optical sensors for heat exist but are pricey.
What about cheaper temperature sensors?
Thermistors are cheap but non-linear. Thermocouples are pretty common, inexpensive, fairly accurate, robust, but need care with connections. RTDs are more accurate but fragile and pricier. Crucial for measuring short intervals. Even cheap stopwatches help, but sensor-triggered timers are better. You can even build DIY timers relatively easily.
Any low-tech tests still used?
The book mentions the palm-of-hand test, basically. Good powder should burn quickly with minimal residue on your hand, but it warns you can get burned.
Yikes. Okay.
There's also a lead tube method, which crushes a lead tube to see if the powder's strength is in a certain range. Chemical analysis is standard for commercial makers, but out of reach for most amateurs. Density can be a rough comparison.
And sieving the grains.
Crucial. Sieve sizing measures the physical grain size. You need consistent grain size for reliable test results. Even commercial powders vary, so testing within a narrow size range is best for comparison.
So it all comes back to consistency, avoiding apples and oranges.
Exactly. Keep your methods the same. Linear burn tests can be okay for comparing your own batches made the same way, but there's no single absolute standard. Best practice is to get a known powder, test it as your baseline, then compare your homemade stuff to that baseline.
Makes sense. Finally, the book included this section, A Visit to GOEX. Tell us about that.
Yeah, GOEX. At the time the book was written, it was the last commercial black powder maker left in North America. Started as the historic Berlin Works in Pennsylvania.
Historic plant.
Very. It almost closed down, but was bought and saved as GOEX. The plant itself sounded amazing. Lots of wood construction, even a wooden railway. Gravity used to move materials, water-filled tubs everywhere for safety.
Wow. Strict rules.
Very strict. Limits on how many people could be in one building at a time. Huge lightning protection system for the storage magazines.
Sounds like a unique place to work.
Apparently had a lot of pride, multi-generational families working there. It started rural but got surrounded by development, though the locals were proud of the tradition.
Is it still there?
The book noted signs of reduced production, and unfortunately, after the book was written, they lost their rail service and had to relocate the whole operation from Pennsylvania down to Louisiana.
Ah, okay. So a piece of living history had to move.
Yeah, underscores the challenges faced by that industry.
All right, the learner. Let's try and bring all this together for you. After this deep dive, hopefully you've got a much richer sense of what goes into black powder.
Yeah, it's not just mixing three things. It's the sourcing, the careful charcoal making, the critical safety steps, the history of figuring out how strong it even was.
It's a simple substance with a really complex story, full of practical hurdles and some pretty clever solutions over the centuries.
And what's really fascinating, I think, is how it went from this, almost accidental discovery to these controlled processes. But we still don't fully understand the chemistry.
That is pretty wild.
So here's a final thought for you to chew on. If something we've used for hundreds of years, like black powder, still holds chemical mysteries, what other everyday materials, things we think are simple and completely understood, might still have secrets waiting to be uncovered?
Ooh, that's a good one. Makes you wonder, doesn't it?
It does.
So, if we've sparked your interest, maybe unintended pun there,
Yeah.
perhaps dig deeper into those old testing methods or the different wood types for charcoal, there's still plenty to learn.
Absolutely. The world of black powder is old, but still full of fascinating stuff.
Indeed. Thanks for taking this deep dive with us.